coming to conservation in a changing climate. We are going to go ahead and get started, although I expect people will be coming in from the poster presentation. Kicking us off is Nicolas Dubois, talking about body size and climate change, assessing the explanatory power of climatic anomaly in temperate songbirds.
Thank you, Nicole. Well, just a word about body size and conservation. I was in Conservation Congress. Why do I study body size, and why do I show up in a Conservation Congress like that? Well, probably because body size is basically can be interpreted as an index of individual quality and and affects survival and reproductive success, and also is involved in thermoregulatory mechanisms and in the resilience in the face of climate change. So let's get started. So as you all know, climate warming is a component of climate change, for which species response is now acknowledged. Species respond through time with phenological shifts. Species respond through space with changes in distribution areas. And there are self-responses as well. For instance, body size decline that was more recently proposed as a third universal response to warming with these brilliant papers. So what's the mechanics behind this? It's not like in the movies. So one proposed that this would be related to temperature and the ability for smaller individuals to better lose the heat. So this is the interpretation of Bergmann's rule. I will just give a few words about this brilliant researcher of his time. So Bergmann's rule proposed that under colder climates, species tend to be larger because they have a higher ability to conserve the heat and suffer less from hypothermia. While in more southern or in more lower latitudes, species tend to be smaller and have a higher heat loss efficiency. And then being smaller enables to less suffer from hypothermia. This pattern also works within species, with, for instance, this little robin at between the north and the south of its range could differ in body size. So what now? Under climate warming, what if with my almighty power I hit the climate in every places? Would all individuals reduce their body size, and hence which would enable them to better lose their heat and less suffer from a hypothermia? So far there is no proof of such thing, and that's why we intend to do. So an alternative hypothesis was that body size reduction would be related to food availability, that itself as a consequence of climate change. For instance, food availability, like for birds, would be invertebrate abundance, for instance, is directly related to temperature and to precipitation. So under warmer and dry conditions, the amount of food available in the systems would decline, which results in a body size reduction. So two mechanisms behind this that are non-exclusive. Is this more related to heat loss efficiency, or to food availability and protein intake? And now, how does this occur? These effects can operate through effects on juvenile growth. And these effects can operate also through size-dependent mortality, with, for instance, in the case of Bergmann's rule, under warming conditions, the largest individuals would more suffer from hypothermia, and then, as a result, in the overall populations, we would observe a size reduction. So my research questions are as follows. What is the driver? Is it rather temperature, or is it rather food availability? And in which is the most prevalent, because both are non-exclusive? And what is the mechanism underlying this? Is it through effects on juvenile growth, or is it through effect on size-dependent mortality, or both? Well, previous research has made many advances, but most of the time based on single species of populations, or one or two sites, and sometimes based on museum specimens. And we propose to test this hypothesis using a multi-species database with a broad range of species sampled over a large geographic scale, like 250 sites across France, and for 15 years of survey, corresponding to an interesting period of warming. My response variable, as in body size, I use Wingleaf as a proxy for body size, and I also test alternative hypothesis if these effects are more applied to body condition. And for my climatic variables, I use temperature to test for the heat loss efficiency hypothesis. And to test for the food availability hypothesis, I use precipitation data and also net primary predictions of remote sensed images, what I call NDVI, and also interactive effects between temperature and precipitation. And I use local anomalies because I want to control for spatial effects, as I use many sites. So I've used modeling approach in which I included all possible combinations of my environmental variables, and I built my inferences on the basis of information theory. So to test for size-dependent mortality, I explored the patterns of size distribution within each population. And here you can see, for instance, on the, do I have a pointer? Yes. On this size, you can see that these are the smaller individuals within the population, on this side, the largest. And I test for juveniles, and I observe whether in this next year, when they are 1 year old, whether this part disappears or not, which we would interpret as potential mortality, or maybe dispersion, but mostly mortality. And then we will look whether, well, in this case, this will be the contrary of Bergmann's rule applied through time, with the smallest individual being more prone to mortality. And I test further whether this is related to my environmental variables. Here's the results. So what are the drivers of body size? I found that the very best model was my proxy for food availability, NDVI, net primary production with a squared effect in all of the cases. So this was very robust and lower extent temperature and temperature interactive effects with precipitation. So here's the effects. Here, this is a GAM version of the previous result. So here you can see the nonlinear effect, the response. You can see here, in years with negative primary production, locally negative primary production, you can see that there's almost no effect. But here, in the positive anomalies, you can observe a positive effect. On the other, and this means the little number 1 here means that this effect is robust to uncertainty. So this means that the effect is certain. Here, the effect of temperature is rather linear. It's positive, contrarily to the expectations from the application to Bergmann's rule through time. And we can see that the statistical support is rather weak, so the effect is uncertain when applied to 40 species over a large geographic scale. And, well, this looks beautiful, but the pseudo R-square is rather weak, only 1%, and so which means that probably that there are other drivers than these variables that may operate, for instance, local drivers or species-specific drivers. This result was kind of data sensitive, as this was obtained with my extensive data set. But when I try with a more intensive data, only 6 species the most common, and keeping only the most intensively sampled sites, the R-square rises up to 13%. So maybe this is related to some statistical artifacts due to the extensiveness and scatteredness of my data. Or this may also mean that only the most common species have observed these effects. So just a word about adults, I found nothing. So the best model was the null model from far, so I'm not even showing you the second and the third model, as it's completely irrelevant. Now, what about, is that size-dependent mortality, or is that through effect on juvenile growth? So I've tested whether there was size-dependent mortality. Maybe there was, but there was nothing to do with my explanatory variables. So we interpreted the effect of NDVI as an effect of juvenile growth. So let's discuss this all. So to answer the question, is that food or temperature or heat loss efficiency? Rather food and protein assimilation that may drive in my system, that is a temperate system. But still a poor explanatory power, and through juvenile growth also. So we found no negative effect of temperature, which is contradictory with these expectations. So we found this in France, nor in Germany, nor in the Netherlands. That's what I've noticed. And in contrary, there was rather a negative effect in Israel and in Australia that are warmer climates. So maybe this is a matter of thermal context. For instance, here, in a temperate climate, a slight increase in temperature, and the species would remain within their thermal tolerances, while here in the tropics, a slight increase, and the species would go beyond their thermal tolerances. So this remains to be tested. So why a positive effect of hotter years in a temperate climate? Maybe because this is related to the fact that temperature gets warmer would result in a metabolic gain for heat maintenance, which enables the juveniles to allocate more energy for body growth. And maybe as well, it could be an indirect effect of temperature on net primary production, as in France, precipitation is not very limiting. So third universal response to warming, maybe it depends on the latitude. And was it juvenile growth or size-dependent mortality? As we did not find any effect on adults, and this little analysis showed that there is no great effect of size-dependent mortality, we presume that effects operate through juvenile growth. And I specify that we are focusing on the breeding period in a temperate climate. So to summarize and conclude, food assimilation seems to prevail on heat loss efficiency, and it may be true mostly for the most common species, which calls for the next steps to look for local determinants for potential demographic effects or species trait dependence. So, and the fact of being small in a warmer conditions maybe invites us to test for a more wider scale and test for a global scale analysis. And that's here that I conclude. I thank all the kind of support. I thank you for attention. I take questions. Thank you.
Unfortunately, we do not have time for questions, but thank you very much. I'm sure you can find him later. Oh, no problem. Figure out the technology here. There we go. Which one is it? Okay, there we go. All right, up next, we have Dr. Reid Noss.
Thank you. Good evening, everyone, and thanks for sticking it out over a long day. Tonight, I'm going to talk about the important linkage between centers of endemism, primarily on a global scale, and this phenomenon of climatic refugia, and what this means for conservation of biodiversity during a time of rapidly changing climate. So if you follow the literature on adaptation to climate change, a large variety of different strategies have been recommended. Probably the two most promising, in my opinion, in terms of biodiversity conservation is first to maintain or restore functional connectivity for organisms across climatic gradients. For example, latitudinal gradients or elevational gradients, so the species can track the shifting climatic envelopes. This has been the most frequently recommended adaptation strategy for conserving species in the face of climate change. A second strategy has not been discussed nearly as much, in fact, hardly at all until quite recently. And this is the idea of identifying and protecting climatic refugia. And these can be recognized at a variety of spatial scales ranging from large regional refugia down to small microrefugia within any given region. Importantly, especially at the regional scale, climatic refugia typically coincide with hotspots of endemism, which has great relevance for conservation. So this talk is based largely on some work I've done with Susan Harrison of University of California, Davis. The two of us co-edited a special issue of Annals of Botany that appeared earlier this year on the relationship between centers of endemism and climatic refugia. And we also authored a introductory paper, which is a review of the subject. This special issue, in turn, was based in large part on a symposium we had at the Ecological Society of America Centennial Meeting a couple years ago. So arguably, if you are interested in reducing extinction rates, endemism may be the purest measure of conservation value of any given region. If you can locate areas that maintain or contain high concentrations of species found nowhere else, and then protect them, this is a very cost-efficient way to reduce extinction. So in line with that logic, and beginning with the work of Norman Myers in the 1980s and 1990s, global biodiversity hotspots were defined based on levels of plant endemism and rates of habitat loss. And as of today, there are some 36 global hotspots that contain at least 1,500 endemic plant species each, and have each suffered at least 70% loss of habitat. The 36th, or most recent hotspot recognized is the North American coastal plain, and this recognition was based on some work done by my colleagues and I for this region. Now, a complementary strategy to protecting these areas that are vulnerable and have high rates of habitat loss is to protect intact areas, ecological intact areas, or wilderness. And maybe some of you saw James Watson's talk in Symposium this morning, which underscored this idea. And Russ Mittermeier and colleagues back in 2003 published a paper where they identified global wilderness areas with human population density of no more than 5 people per square kilometer, and were more than 70% intact. In fact, most of them well over 70% intact. However, only 5 of these regions met the endemism criteria for a global hotspots. But these are very important regions, of course, because not only do they have these essentially equivalent rates of endemism, but they're also intact, so that you might be able to actually preserve them more easily and over a longer period of time. So the wilderness areas that meet that criterion are, the criteria of high endemism are outlined there in red. And an example of one of those regions in North America, Mexico, and the USA are the North American deserts. And these deserts hold some 5,740 endemic plant species, which is extremely high for a temperate to subtropical region. And these are very lightly populated regions outside of the cities. So what is some of the evidence in support of this coincidence between centers of endemism and climatic refugia? Well, first, there's paleoecological evidence, such as fossil pollen as well as macrofossils, which shows relatively low rates of climate change and vegetation change over time in global hotspots of endemism. Now, admittedly, not many of these hotspots have yet been studied with respect to this question. A second line of evidence comes from molecular studies looking at Pleistocene refugia at various places in the world, where they have found hotspots of both genetic and species diversity within presumed climatic refugia. The paper cited here was one done for the Peruvian Andes by Carnaval et al. But it really goes back, these refugia go back much further than the Pleistocene, something that isn't discussed much in the literature. There's evidence from several regions around the world that they have been relatively stable for tens of millions of years. And so, for example, regions such as the North American coastal plain, southwestern Australia, the Cape region of South Africa, and Amazonia have changed relatively little in climate, and we're protected from these post-Eocene changes of including aridification, cooling, and climatic extremes that started taking place about 40 million years ago. But here we find a paradox. There's abundant evidence suggesting that climatic oscillation actually promotes speciation. So for example, climate change, in many cases we know, generates novel habitats, new niche space, if you will, which is then exploited by species and promotes speciation. In addition, climate change often results in shifting patterns of habitat isolation, which is conducive to allopatric speciation. And sometimes these lineages come back together and we end up with hybridization, which in plants often leads to even further diversification. However, these newly evolved lineages are not likely to persist long unless there's some moderation or amelioration of these extreme climatic oscillations. So here's where the refugia idea comes in again, and especially then for paleoendemics, the final bullet here, climatic stability over a long period of time enables persistence of these ancient lineages. So as an example, the most newly designated global hotspot, the North American coastal plain, of the endemic genera of plants, some 77% of the 56 endemic plant genera are monotypic. Monotypic genera are typically, in fact, almost always ancient taxa, as far as evidence suggests. Serenoa there at the top, we have fossils of that dating back to the Eocene, for instance. Interestingly, many of the global hotspots, in fact, most of those that have been studied, actually contain a mix of both paleoendemics and neoendemics. The old taxa tend to be associated with those geologically and climatically ancient habitat types, whereas the neoendemics are associated with more recently developed habitats due to fluctuations in sea level, geological change, and so on. And so any given hotspot region can be both a cradle of high speciation as well as a museum of low extinction, using the terminology of Stebbins. Another strong generalization is that most global hotspots of endemism are mountainous regions. The mountainous topography enables species to track shifts in climate over relatively short distances by moving upslope or to a different slope aspect or soil moisture condition or whatever. And so the reduced climate change velocity associated with mountainous regions can predict richness of small range species on a global scale, as shown by studies by Brody Sandel, for instance. And two of the hotspots that meet that generalization are shown here. But being mountainous is not the only reason to achieve climatic stability and maintain high endemism. Another factor is proximity to persistent or consistently warm or mild ocean currents. And of course, we find this in islands, we find this in Mediterranean regions, and other regions around the world. And again, the North American coastal plain, where I happen to live, has very high climatic stability going back tens of millions of years, despite being extremely flat, the flattest of all the global hotspots. Now, throughout this talk, I've been mostly discussing these regional climatic refugia and centers of endemism. Also, very important, and just newly recognized to the conservation community, it seems, is the importance of micro-refugia, which are not limited to these global centers of endemism. You can find micro-refugia in essentially all regions worldwide. And basically, these are habitats that are out of equilibrium with the regional climate, maintain unusual conditions for that region. An example would be karstic depressions, such as sinkholes, which maintain cooler conditions during the summers or during warm periods and warmer conditions during cool periods. So in conclusion, the strategy of protecting hotspots of endemism is well established, generally well accepted within the conservation community. It becomes even more important and urgent in a time of rapidly changing climate. I think we can agree that it's good news that we have this overlap between climatic refugia and centers of endemism, because it means we can meet many goals simultaneously: biodiversity conservation, climatic adaptation, and so on. Nevertheless, we can't be complacent at all here, because Although extinction rates within these climatic refugia are expected to be quite low compared to non-refugia, the absolute rate of extinction could still be high if the rate of climate change or other threats such as habitat destruction, which after all is still a bigger threat to biodiversity than climate change, is particularly high. A major concern is that species associated with stable climates may have many stability-associated functional traits, which make them more sensitive to rapid climate change, such as narrow climatic tolerance, poor dispersal capacity, low rates of dormancy, high habitat specialization, or low genetic diversity. Thus, if change is severe enough, either in habitat loss or climate change, our hotspots of endemism could potentially become hotspots of extinction. And finally, we do need more research to determine the location of these microrefugia in all regions. They're not easy to identify necessarily, unless you have a lot of really good field naturalists out there, because they're not included in most GIS layers, which are too coarse. And therefore, they're not included in most species distribution models, including climate envelope models. Thanks very much. Am I out of time? I guess I can take one or two questions if there are some. Paul.
Just on that very last point, there is Chris Daly, the inventor of PRISM, there are some algorithms that might help identify some of those microrefugia.
Cool.
He has an algorithm for identifying areas of full air cooling, which could be decoupled from regional climate. So
Very
that's
cool.
one type of-
Okay, so the PRISM climate model might be an exception.
Yeah,
Very
well,
good.
it's not in the PRISM. It's a separate thing.
Okay,
It's
okay.
The same guy who developed
Got it,
PRISM.
got it.
Yeah.
Thanks.
All right, and I'm afraid we got to cut it off there.
Okay,
Thank you
I
very
understand.
much.
Thank you.
It's 12 minutes passed pretty quickly. Okay. Let me get the next one. Where's the technology? Okay. All right. Next up, we have Daniel Thornton speaking on climate change adaptation for mammals challenged by asymmetric transboundary protection.
So before I start, I just want to quickly acknowledge my co-authors, Dr. Lynn Branch from the University of Florida and Rosemary Rodriguez, a student at the University of Florida, that really helped tremendously bringing this analysis together, largely under a time crunch that I was responsible for. So I owe them dearly. So transboundary conservation efforts have really been steadily growing over the past couple decades due to really increasing recognition that maintaining intact, connected, functional ecosystems requires large-scale planning and management that crosses political boundaries. So growth of transboundary protected areas, regional initiatives like Y2Y and various corridor initiatives really attest to this growing trend. Nevertheless, political boundaries continue to impede conservation due to a lack of coordinated action and management. And when we bring in climate change to this question, it sort of adds to the urgency of thinking transboundary. We know that species are going to shift their range, and those ranges are going to expand and contract, probably with a bias towards poleward and upward elevational range shifts that we're already seeing. And those range shifts will be occurring against a backdrop of international boundaries. That's really going to challenge our ability to have coordinated management and conservation for those species. At the species level, conflicting and diverse national priorities for conservation can sort of add other layers of complexity. And one way that can happen is through these asymmetric listings of species across international boundaries. So as an example of this, we see here one of my study species, Canada lynx, a mesocarnivore with a range that extends between Canada and the US. In the US, the species is listed under the ESA, Endangered Species Act, as a threatened species. In Canada, it's unlisted and managed as a harvested fur bearer. And there's substantial harvest of lynx, even in areas immediately adjacent with the US border, which could potentially threaten our ability to recover and maintain US populations of lynx. So these sorts of asymmetries in listing can potentially be problematic for maintaining robust range-wide persistence of species, and could also be important in thinking about climate change adaptation. For example, you could imagine if habitat suitability is shifting poleward into an area where protections are lesser, that could potentially challenge the ability or the rapidity with which that range shift could happen. So we wanted to, kind of using links as an inspiration here, we wanted to sort of delve into this question of transboundary ranges and listing status at sort of a broader scale, using all mammals in the Americas as a case study to look at this question. And in light of potential impacts of climate change, we were very interested in looking at the transboundary nature of ranges from pole to equator. So the two main questions then for our analysis here are how many mammals have their poleward and equatorial ranges located in different countries, and what's the conservation status or level of listing given to those range limits at the national level. And then how common is asymmetric protection of those species, where we see listing, say, in the equatorial range but not the poleward range, or vice versa. And then which of those sites tends to be the area of stronger listing. And one caveat here really quickly, I'll be talking a lot about listing of species at the national level, and we're aware that listing does not necessarily equate, listing a species as endangered or threatened does not necessarily equate to level of protection, but we argue that at least it's a starting point along the line to greater protection and attention afforded that species. So methods are fairly simple here. We overlapped IUCN range maps for mammals in the Americas with country boundaries. And identify the poleward and equatorial ranges. So for example, the smoky bat here has its equatorial range in Ecuador, its poleward range in Chile. And we did this for all mammal species. And obviously this is just identifying the extremes is a vast simplification of the transboundary nature of mammal ranges that can extend through 3, 4, or more countries, but gave us a starting point with which to work. Then we collated national level lists of threat status or conservation status for species across all countries in the Americas. These come from various time periods and sources, but we brought them all together, and because there's different ways to categorize species in different countries, we kind of developed some rules to collapse those into endangered, threatened, and special concern categories that we then used going forward in our analysis. So we brought the range analysis together, the protected area analysis, the listing analysis together, and then from that we could determine the percent of mammals that had listing in their poleward or equatorial range limits, and we could identify then the asymmetrically listed species. So for example here you see the smoky bat is endangered in Ecuador, not listed in its poleward range in Chile, example of an asymmetry in listing, with the reverse situation here for the howler monkey, threatened as pole and not listed in its equatorial range. So when we do this across all mammals, what we find is a fairly high percentage, about 50% of mammals are transboundary in their ranges from pole to equator, meaning their poleward limit falls in a different country than their equatorial limit. And of those, about 860 transboundary mammals, about more or less 30% show this asymmetry in listing status. If we just confine that analysis to transboundary mammals that are high threat IUCN, so vulnerable, endangered, critically endangered, that jumps to around 50 or 55% show that asymmetry in listing. In contrast, very few show kind of equal listing status at a national level across that poleward and equatorial limits, and obviously a lot of species don't have listing in either range. So listing in both range edges tends to be low, but there is appear to be a slight bias towards greater listing status at the national level for those equatorial limits. And we can kind of look at this in a couple of different ways. We can say across all transboundary, all 860 transboundary species, is the pole protected, is the equatorial range protected at the national level. When we do that, we see about 21% equatorial protected or listed, 16% poleward. If we can find that to high threat IUCN, we see a slightly greater bias with 61% listed equatorial and 47% towards the pole. And that's not just North Pole, that's poleward north or south. And then finally, if we just take those asymmetrically protected or listed species and ask the question, which side has the greater listing status, we see kind of a similar level of bias there with 60% having the greater listing towards the equator. So what can we kind of draw out of this? There's a lot more to do here, and I always hesitate to draw strong conclusions from these kind of broad scale pattern analyses, but I think we can look at a couple of different issues. First of all, the high percentage of transboundary mammals that we have, the high number, and the number that are actually asymmetrically listed leads to questions regarding what's the significance of that asymmetries in listing status. Does it have the potential to reduce robust range persistence, connectivity across international borders, disrupt source sink or metapopulation dynamics? So going back to that example of lynx, where we're working, well, the big question there is, does harvest in the unlisted areas in Canada adjacent to the US border impact dispersal and connectivity of lynx coming into the US that could be used to bolster the US population? And so thinking about those sorts of issues, but at a much broader scale, I think is really important. And also, in the context of climate change, we really need to understand this, these lower levels of listing of these poleward range segments. What's driving that? Is it a range size issue? Idiosyncrasies with the countries that we're looking at? And if listing does reflect some degree of protection, what's the significance then of having these lesser listings in the poleward populations? You can kind of look at it two ways. Potentially, it means those populations are more robust, which is good in the context of climate change. On the other hand, it could mean that those local poleward populations are receiving lesser protections, in which case that could challenge their ability then to serve as fronts of range expansion and persistence in the future as the climate warms. More generally, I think this points to the need for sort of greater consideration of transboundary status of species and national level priority setting exercises in terms of research, management, planning, etc. Again, using kind of our lynx example as a case study of this. So we've actually brought together a team of transboundary land managers as well as academics in the Washington, British Columbia region that you see up here to actually start a couple of transboundary projects looking at lynx distribution and movement in the transboundary area. And also involving some of the key stakeholders that play into this, in particular the fur trappers in southern British Columbia. And so I think that kind of coordination can go a long way to thinking about the consequences and our ability to ameliorate these listing asymmetries. And obviously taking advantage of mechanisms that are out there for increased transboundary collaboration, whether those be transboundary protected areas or some of these organizations like landscape conservation cooperatives that we have in North America that work across borders to coordinate efforts. And I think I am out of time, and I'll just leave you with a picture of an environment very different from here, but it's near the US-Canada border where we're doing some of this lynx work. Thanks.
All right, thank you, Daniel. And, okay. Oh, I see. Okay. Okay. Good enough. Gracias. Next up, we have Annika Keeley speaking on prioritizing connectivity to facilitate range shifts.
Thank you, and thank you all for being here. Good afternoon. So species have already begun to shift their ranges to adapt to recent climate changes. To facilitate these range shifts, we need to provide permeable landscapes. Because of limited resources for conservation, we have to prioritize where connectivity conservation is most urgent. As part of the fourth California Climate Assessment, we reviewed the literature on methods or approaches that prioritize connectivity to facilitate range shifts. And while habitat connectivity has been a conservation strategy for over 4 decades, climate-wise connectivity adds a new dimension. So how do habitat connectivity and climate-wise connectivity differ? whereas the objective of habitat connectivity is to support wide-ranging species and enable dispersal movements, climate-wise connectivity aims to facilitate range shifts. And whereas habitat connectivity aims to connect similar habitat, climate-wise connectivity aims to connect climate analogs, current to future suitable habitat, and also land facets. And then, whereas habitat connectivity is usually designed for wide-ranging species and species that occur in metapopulations, climate-wise connectivity needs to be designed for species that need to shift their ranges with climate change. There's generally no directionality in habitat connectivity, except for species that depend, for example, on dispersal through water. But climate connectivity needs to take temperature and moisture gradients into account. And whereas habitat connectivity is designed to avoid steep slopes, usually, in climate-wise connectivity, slopes are advantageous as climate gradients. And a high diversity of geographical or geophysical features provide microclimates, microclimatic diversity, which sustains survival despite climate change. And that's what Riednas was talking about with the refugia. And the temporal scale there varies as well, whereas habitat connectivity is focused on the present, thinking about daily movements, dispersal movements over days, weeks, or months. Climate-wise connectivity plans for the mid to end century, mid to the end of the century, and considering multiple generations. And finally, the spatial scale is different. Whereas habitat connectivity is planned at the local and regional scale, for climate-wise connectivity, we need to think at regional to continental scales, but we still need to act locally, but we need to have the continental scale in mind. Because of these differences in scale, in the literature, what I found is that the line between connectivity conservation and general biodiversity conservation has become fuzzy. To facilitate range shifts of all species, a network of large reserves embedded in a permeable matrix and connected by wide corridors or linkages or stepping stones is described as the ideal scenario. An increase in habitat amount, an increase in habitat quality are as important probably as habitat connectivity. We need to think of all these things simultaneously. So with these differences in mind, we searched the literature for connectivity modeling approaches that focus on integrating connectivity and climate change science. We found 96 relevant papers, 67 of which were original studies, and 29 were review papers or essays. We extracted data from for a set of categories from the original studies, and then performed a cluster analysis to help us with grouping these papers in a logical way. So the cluster analysis yielded two major groups. The upper one, there we go. This group here assesses connectivity under climate change, and this larger group here designs connectivity under climate change. And then both groups are split again by studies that use a focal species approach in this group here, and then studies that look more at structural connectivity, these two groups here. And the design studies were again split into studies that look at temporal connectivity and the ones that do not look at temporal connectivity. Today I will focus on approaches to designing climate-wise connectivity only. Oh, what's happening here? There we go. Okay, so a large number of analysis methods have been developed to map linkages, which speaks to the creativity of scientists. I found that quite amazing. Everything from just using the shortest Euclidean distance between two reserves, riparian corridors, of course, least cost path or least cost corridor methods, which were the most commonly used analysis methods. Also graph theory, individual-based methods, climate gradient corridors, land facet corridors, systematic conservation planning. All these methods have been developed to design connectivity under climate change. And these methods vary greatly in data requirements, from anything from just using expert opinion or the shortest Euclidean distance, where you really just need the locations of reserves, to very data-intensive species distribution models or individual-based models. We grouped the different approaches into 11 categories. And you can see the number of papers that go into each category. And I want to just briefly, very briefly, present a few of them so you have an idea how they differ. So some modeled current and predicted ranges of individual species. Here in the top was the Mojave ground squirrel, or of thousands of species throughout the continent. And here you get a very clear idea of what the current range of the species ends right here, and the future one is predicted to be here, and then they have a least cost path in between. And here they had literally thousands of vertebrate animals, and you get a theoretical idea of where the flow patterns will be with climate change. Some studies planned reserve networks for focal species, taking climate change into account, and actually showed how the reserve system should change over time. Some methods relied on environmental gradients. In this example here, these are climate analogs, so current suitable climatic habitat, and here's the future habitat, and the corridor, instead of going essentially through the valley, is designed so the species can live in the corridor while over generations they are moving to the new suitable area. The regular lattice network is designed along mountain slopes and is using the river corridors and then perpendicular design corridors that go south to north. Other papers relied on geomorphic features, for example, land facets, and these corridors try to maximize the diversity of landscape units that are characterized by topography and soil. And then other methods rely on human footprint data. So they're connecting natural areas of high naturalness, and either between just reserves or between natural areas, or now in a new application using climate analogs to connect them through natural areas. And then some modeled connectivity through time, trying to ensure that in every time slice, suitable habitat is reachable. So when do you use which of the approaches? One thing to consider is, as I mentioned, data requirements. What data are needed? What data do you have? Another aspect to consider is your objective. For threatened or endangered species recovery or focal species movement, the species-based approaches are probably most appropriate. If the objective is to facilitate range shifts of the whole biota, then the structural connectivity approaches may be more suitable. To consider ecosystem resilience overall, the protected area network planning specifically with connectivity modeling as part of it can be used. And then in a very different objective, in addition to climate adaptation, one paper tried to increase climate mitigation too by finding the corridors that have the largest carbon sequestration rates. And so we have the objective data requirements, and then also the level of uncertainty and the level of specificity varies between these approaches. So here they are ordered from low to high, and we have the low specificity approaches down here, high specificity for the species approaches here because they are really modeled for specific species, but the uncertainty is reversed. So we have low uncertainty here and high uncertainty in the focal species approaches because they often come with models that include uncertainty. In terms of future research, not many studies have addressed land use change. And then we should account more for the effects of landscape heterogeneity, getting again to the refugia. If there would be a way to evaluate structural connectivity corridors for climate change, that would be amazing, if somebody could figure that out. And then method comparisons would help, because I only found 6 papers that used more than one approach. All right, and thank you, and I hope you have time for questions.
All right, thank you, Annika. Okay, next up we have Adina Marenlander talking about the barriers and opportunities to implementing connectivity on the ground.
Move this down a little. I am vertically challenged. All right, great. Well, my advisor's name is Andrew Dobson, and he actually taught me to always be in the bar by 4:30 at any Congress. So you guys are in the wrong room, but I thank you for it anyway. So the question that we're really going to be focused on for the research I'm discussing today is, what are the barriers and opportunities to implementing connectivity on the ground? This, like Annika's work, is part of the California's 4th Climate Change Assessment. And like Annika's work, was done by Annika. So thanks, Annika, for doing more literature research. But this time, rather than focused on methods, her literature work focused on implementation. So what's happening? What do we know about how people are actually putting corridors on the ground that we can see and walk through? So the search actually involved, similar to the methods, a search of Web of Science and Scopus, but also because we were expecting more informal reports and project reports, we also did a Google search. And it revealed 24 peer-reviewed papers focused on implementation and lessons learned, 15 reports, and 5 book chapters. Now, this is really pales in comparison to the 96 papers that Annika was able to address just on climate-wise connectivity. If we just looked at science done for habitat connectivity, it would probably be tenfold the amount that she found for climate-wise connectivity. So really we don't have a lot to draw on. However, the folks that did write these reports and papers had some critical elements to share with us that they thought would be keys to success in really getting conservation done on the ground. And those included a shared vision with the community and the team at work on the linkage, working at the correct operating scale. So for this, authors were saying that would be at a regional scale where there's a similar sort of socio-ecological context, and yet at the same time having data at the parcel level scale for implementation. Building and leveraging on social and economic networks is obviously important in getting things done. Charismatic leaders was mentioned by more than one group of authors, and these will be people who can really stay with the project and have leadership until the entire thing is done. Species focus was emphasized as well, communication, funding, and they also suggested a few tips that we should think about. One group really felt strongly that the delineation of the edges of the linkage being proposed to the community should not be strict and explicit, but rather somewhat fuzzy. In other words, so people don't feel sort of definitely in or definitely out. So that was an interesting piece of advice for us. And also focusing on early successes. These might be small restoration type things. Get people engaged early because some of these projects can go on for many decades. All right. So, and the other thing that there was a little bit of a trade-off going on between different authors in the literature was that some folks were saying regulations are a terrible idea. These private landowners don't want to be regulated into participating in linkage conservation. Others were saying without regulations and mandates, you know, agencies and NGOs and stuff, it's hard for them to engage. So we didn't have a lot of literature coming out of California. Rather, there was quite a bit coming out of Australia and Europe and other places. And we also just didn't have a lot of literature to start with anyway. So we went with the workshop model, an NC's workshop this past year, as well as interviewing 30 practitioners from California to get sort of a California picture. And based on the interviews and the workshop, we ended up discussing over the past year basically 24 California corridor projects. And I just want to note that out of these 24, 14 were primarily motivated to set up a landscape linkage to address habitat loss and fragmentation, whereas 4 were more about mitigation, infrastructure, transportation, which can be sort of integrated. Endangered species was another motivator for a couple projects, and climate change. However, 4 additional projects also mention climate change. And of course, most projects had more than one sort of justification or ought for why they were being done. With all of this, the literature, the workshops, the interviews, we ended up putting together collectively among many collaborators as part of this 4th assessment project. And Sam Velas is in the audience, so some of the folks are here, which is great. A framework for this kind of our understanding of the research we did here. And the framework involves a socio-political ecological context that surrounds the entire implementation effort, right? That influences everything that's going on. It involves partners, who's at the table, so NGOs or private sector partners, government partners, academics. And then really the core elements of this framework that I would like to focus on is the planning, and then, so the planning phases, which involves ecological work and data analysis, but also opportunities and challenges that the corridor projects faced, the implementation strategies or the toolboxes they actually use on the ground, but all of it together with the same focus on the desired conservation outcome, which is more proximately an actual corridor, right? Or stepping stones, permeable landscapes, the kinds of things we're used to thinking about, and ultimately to increase population viability and facilitated range shifts. So let's dig a little deeper into those 3 core elements of the framework and what we've learned from the projects, which is that in the planning phase, there's kind of 2 issues that they're dealing with. Often it's a focal species movement or endangered species, and then the second 2 more climate considerations, so range shifts and resilience to climate change. And just to illustrate this point, I want to bring out the Coyote Valley landscape linkage. This would be south of San Jose, for those who haven't been there, Silicon Valley. And the last remaining pinch point between the Santa Cruz Mountains, the Coast Range, and the Diablo Mountains. And what we see going on here is a lot of species focus, a shared and collective vision. They have a new vision document out talking about the species that move through this valley, camera arrays, data on underpasses, genetic studies, so all kinds of collaborations with scientists to really look at this focal species movement as their primary issue. I mentioned that also in planning, of course, comes the work that most of us do as conservation biologists, which is the collecting of data and data analysis. So the favorite types of data, tracking, camera, roadkill data, people really want to have more biological information. They really recognize that this was very limiting. Now, this is probably is biased by being in California, where we have access to a lot of distribution models, corridor modeling, climate models. So the people we're interviewing probably felt like they had all the models they needed, but not so much information from the wildlife species they're working on. The challenge and opportunities that they faced, and I already went over lack of biological information. Of course, no one has enough time or money, political support, and dealing with rapid land use change in California. I want to just jump to a few of the opportunities, particularly with respect to transportation. Now, we like to think, we all know that transportation creates barriers to habitat connectivity, but I was really impressed with the interviews of people who work for our transportation department in the state of California, the things they've been doing since 1976, dealing with warning signs and fixing underpasses, exclusion fencing, so all kinds of tools in their toolbox to try to minimize roadkill and improve connectivity. And I just had to share this quote with you by Ted Zolli, who's an award-winning chief engineer in the United States, and he said, "We spend $8 billion per year running over wildlife. If we took that cost and just quartered it, we could build 200 animal crossings a year, and the problem of roadkill would disappear within a generation." So I think we can think about, of course, better transportation planning, but we really can see transportation not just as a barrier, but as an opportunity. I want to talk a little bit about the implementation, that last part of the core elements of the framework. In particular, illustrating it with a project that my lab's been involved with in north of San Francisco in the Sonoma Valley. Here we're looking at a project that in the little red part in the middle is a pinch point of a larger identified linkage between the coastal ranges of Marin County to the Blue Ridge Lake Berryessa interior ranges. And I'm going to illustrate some of the things that you see here where there was land protection opportunities, so that's part of the implementation strategy. There's habitat restoration going on in this area. There's engagement with the public and a shared vision. There's issues around transportation, and they're not actually dealing with land use policy, but it illustrates many of the points that are in this larger list that came from the interviews in the workshop. So here's just a little zoom in of the linkage. It's going, as I said, from Sonoma Mountains to the Mayacamas Mountains, but it's in that pinch point of a much larger linkage across a valley with vineyards and transportation. I want to mention in particular that while a lot of work had been done on this linkage and camera arrays and putting cameras under the road culverts, so there had been lots of sort of biological information, our lab also looked at the climate benefits of this particular pinch point. And surprisingly, what we show here is that if you look at the climate, the average annual climate over 30-year periods for the range on the west as compared to the range on the east, so these are the two ranges that we're trying to connect, you'll see that we have substantially lower summer temperatures in the range on the left. So basically, if a species were to do a shift between the eastern range, which is quite close, you can walk in an hour across this linkage, they will gain 3 degrees, or in the future 2 degrees cooling by shifting from the eastern range to the western range of this linkage. So this pinch point has very dramatic differences in climate. And the opposite trend for winter, which is an interesting phenomenon of California because we have a coastal influence. So cooler to go to the east in the winter, cooler to the west in the summer. And lastly, I just want to say that there's a lot of activities. Remember that the authors in the literature suggested some early successes. And in Sonoma Valley, lots of restoration going on, public engagement, controlling people's pets, dealing with recreation, fencing, so all kinds of on-the-ground toolbox strategies that are going to help to maintain connectivity across this important linkage, in addition to the acquisition of the land. So all in all, we leave you with a much more complicated framework than we started with, but all this framework is doing now that we hope to publish soon is fleshing out the information that I've shared with you for these various key elements and putting it all together. And of course, we're all ecologists, so we had to add monitoring and evaluation in there and that adaptive feedback loop. And with that, I thank all of our partners in working on the Fourth Assessment Connectivity Project. And thank you for staying out of the bar for a few more minutes. I'll see you there.
All right, thank you very much. Oops. Okay, next up we have Boris Tinoco, talk about bird community change across space and time in an Andean high elevation national park in Ecuador.
Thanks everyone for being here. For sure, many of you would prefer to be out having a beer in Cartagena, so thanks for staying this late. So this work, as a difference with the other work that was presented before, it's using data set from a field work. And it's part of a collaborative effort among many different people and institutions. And I will be exploring how a bird community is changing in a national park in the Andes of Ecuador. So we know that communities can change in space and time, but understanding the dynamics of the drivers of that variation is key to have better predictions of the responses of biodiversity to environmental change. And this is shown here with just two graphs, one showing how how biodiversity is changing across time, and the other one showing how the number of bird species richness is responding to a habitat disturbance gradient. And there are many different methods that we can use to calculate community variation. The most common one is species richness, the number of species in a given area or time. And the problem with this measure is that if there is compensatory dynamics in the abundance of different species, that would result in a pattern of stability in species richness across time. That's why other measures of communities, such as turnover, which incorporates the identity of species, can be highly informative about the responses of biodiversity to different ecological factors. So here I will show you how a community is changing in measuring species richness and community composition or community of birds using a moderate long-term data set from Cajas National Park in the high Andes of South Ecuador. This is a map of the study area. The landscape here has been transformed for many centuries, and now the remaining forest is very isolated and is located in very inaccessible areas. So we're working in areas that were originally mountain forest. So we work in 3 different habitat types: a native forest, an introduced forest, which is composed now by eucalyptus and pine trees, and a native shrub habitat, which is recovering from previous cattle grazing. So we've been sampling birds in those habitats for 10 years now, covering the seasonality in the weather in the study area, and we are capturing and banding birds to keep track of recaptures. So now some results after these 10 years. So first, we found that the number of bird species is greater in the introduced forest or the shrubs compared to the native habitat. And that's interesting because it's showing that these secondary habitats perhaps are providing some conservation opportunities for the species, at least in the region where we work. So looking at the community composition and how that varies among these 3 different habitats, we found first that each habitat has a particular set of species. And this highlights importance of the native forest, because as I told you before, there are just a few remnants of this forest type in the region. So if the native forest is lost, for sure many species will be facing some serious conservation challenges. So now looking at variation in time. So far we haven't seen any directional change in species richness in the last 10 years. So species richness is not decreasing nor increasing during the last 10 years, and there's not a trend. There's a lot of variation, but not a trend. But yeah, that's with species richness, but how about with species composition? So to measure a change in the species identities, you can measure the rate of change in community composition using a time lag analysis. And how you do this analysis is that you calculate the difference of the dissimilarity in species composition in a community across the increase in time lags. And then you can explore that variation. If there's just like a stochastic variation, you would see a graph like you have the one that you have in your left, where there's no any particular relationship between the time lag of the samples and the dissimilarity in species composition. Or you can find a trend like the one that you see in your left, where you see where the further apart 2 samples are in time, the more dissimilar they are. So we did that. We explored this analysis in the different habitat types that we are working, and we found that the communities are changing they have a directional change in the native forest and in the native shrubs. And this was significant doing some permutation analysis there. And there are many factors that could be influencing the variation. So species richness is not changing, but the identity of the species is changing across time. And there are many drivers of this that could be influencing that change. And those drivers can operate at different scales and influence those changes. So for example, if local drivers are influencing the changes that we found, you would expect that the vegetation structure would modify the availability of different resources for the animal species, and that would change, or that would produce a change in the community composition of species grouped by different diet guilds. If there are regional factors influencing the change, you would expect that, for example, land use change, we know that modifies the availability of different land cover types in the landscape, and you can predict that that would modify the composition of species grouped by different habitat preferences. And at the end, if there are global drivers influencing the change, we know that climate change is shifting the distribution of species across the elevation range. And if that's the case, you would expect that the community composition of species grouped by different elevation range preferences would be modified in a local community. So we did that. We calculated the rate of community change of species grouped in different ecological characteristics, and that this is what we found. First, we found that the composition of species grouped by different diet guilds show a trend in the native forest. And perhaps this is likely driven by local factors influencing the community change in this type of forest. We also found that the community of species grouped by habitat preferences showed a trend in the native forest. So this could be likely attributed to some regional factors such as land use change influencing a shift in the species and the distribution of species in this landscape and in the native forest. And if you group species by specialization in elevation range, we found a trend again in the composition of species in the native forest. And perhaps this is driven by global factors influencing the distribution of species in the landscape and influencing the community composition of species in the native forest. So it's really surprising to us at the beginning because we thought that the native forest was going to be our more stable habitat compared to the native shrubs or the introduced forest. You would expect that those will be less stable and will be changing. But we found these results in the native forest, so we found the opposite to what we thought at the beginning. And this is really interesting. So in the native forest, the species richness is not changing, but the composition, the identity of species that are part of the community is changing. So to conclude, we saw that modified habitats can sustain multiple species, at least in the landscape where we work. Species richness has not declined during the last 10 years, but the identity of species composition is changing. And this could be driven by multiple factors influencing this variation and promoting these changes in community composition over time. And this also shows that it's really important to have long-term data set to understand how communities are changing. This is really a unique data set. There are not many monitoring efforts in the tropical Andes, a global biodiversity hotspot. And that's really a challenge for conservation practitioners, because if we don't understand how the biodiversity is responding to the environment, it's really hard to have good management practices for conservation in the region. And with that, I just want to thank some of the funding sources, and I'm open for questions. Thank you.
And we do have time for several questions.
Thanks for the talk. That was really cool. I guess this is just a more broad question about the data set. Like you said, this is a very unique data set to have in this area. What you've got individually banded birds, and what other type of information are you collecting on them? Do you have morphometric data? Are you collecting things like that as well?
Yeah, we've been collecting morphometric data. And the last 5 years, we're also collecting pollen samples from hummingbirds, so we're keeping track of what they are using. And this is like the first exploration of this data set. We just submitted a paper looking at survival analysis of the different bird species. So for sure we will be producing more information this coming months or years.
Very cool talk, thank you. You mentioned that in the native forest, species are changing their identity. So can you give a couple of examples of which species are not present anymore and which are more abundant now than 10 years ago?
So there are a couple examples of particular species that are not present. I know a couple of species of tanagers. So here I use like more like a community composition approach. So I'm looking at how different groups are changing. But yeah, we see at least a couple of species of tanagers that are like habitat specialists, the species that are really that you only find in the transition between forest and paramo. We have a couple of those species that we haven't caught in the last years and were like common before. Yep.
One more.
Hi, thank you. It's really interesting to see the change in natural forests just over 10 years, and I'm just wondering, you said that there's something driving that change, and I'm just wondering if you can say what your best guess is at this time.
At this time, I would say that this land use change. It's a tough question because we don't have data about the weather. There's not really many weather local stations, so we don't know how much the weather has been changing. We can use those those broad data sets, but the scale where we're working is really small, so that wouldn't work. But we have data for how the landscape is changing, and for sure it is. The forest is still being cut down, and we think that that could be one of the main drivers of shifts in the distribution of species in our landscape. So land use change, I would say that is as just my personal bet. Thank you.
Okay, thank you very much. Last, but most definitely not least. Control L, thank you. Learn something new every day. Okay, we have James Forrester talking about changing climate and landscapes. Oh, gosh. Tech. Scope. Sure. Oh, because it's a PDF.
Tell you what, I'll deal with it. I got it.
Okay.
Oh, it's in Spanish, though. Can you just share the display instead of having a second one? No? Okay. I can do interpretive dance too. All right, thanks y'all. I'm going to give a talk today about a project I've been working on for the last few years with my graduate student, John Barini, where we're really interested in how, what's driving a very steep decline of moose populations in northeastern Minnesota, an area that's really at the limit of that species' bioclimatic range. I want to acknowledge right up front that this is really a very broad effort, including my postdoc, Althea Archmiller. I also want to acknowledge a lot of partners in state, federal, and tribal agencies, as well as our funding sources, especially the Environment and Natural Resources Trust Fund. So all animals interact with landscapes at different spatial and temporal scales. And what this moose here is interacting with in springtime when things are leafing out is a lot different than what it might experience in the wintertime. And as animals are going across landscapes trying to extract resources, they're doing that in a landscape that is changing. Okay, this is housing density past and future as it might spread across Minnesota, but also forest industries are changing through time as well. And these can have profound impacts on wildlife species. And of course, all of this is going on in the context of climate change. And so this really sort of drives a very straight up conservation and management need. How do we make predictions about how animal populations will respond to novel landscapes and climates? So in Minnesota, this is northeastern Minnesota on the left here. This is the primary range for moose in the state. They surveyed this annually since about 2005, and you can see that that is not a very optimistic population curve from those estimates. But what we don't know, because this is sort of a region-wide estimate, is there some fine-scale heterogeneity that's being driven by differences in landscape quality in those areas? Are some places doing well and other places not doing well? Right now, we don't know that. So how can we build mechanistic links between local population dynamics and the distribution of resources? Well, as moose move through their environment, they're exposed to a lot of different stressors. I mean, these guys are really built for very cold climates. They don't do well even in northern Minnesota. And I would argue that one of the things that sort of influences a lot of those, the direct impacts of those stressors is the availability of forage, high quality forage, and thermal refugia. And I would further state that it might be that not just the amount of those high quality resources, but also the distribution and how they're intermixed in the landscape. Perhaps being a more mixed landscape would be easier for animals to extract resources than that more homogeneous landscape on the right. So where did the data come from? This is the area that gets surveyed. Each of those blocks is about 8 by 4.5 kilometers in size. And each year they survey about 45 to 52 of those by helicopter survey. And those are sort of, the sampling is stratified, where it goes from terrible at 0 up to good at 3, which is the light green. And then the number 4 strata are these places that they resample every year, so you get a good idea of what it looks like as landscapes change through time. And if you look on the ground, I mean, this is a really heterogeneous landscape. This is from Landsat, the National Land Cover Database in 2006. There's lots of lakes, lots of mixtures of different kinds of cover types. And if you go into each of those survey units, you can actually summarize what's going on. Here we've summarized the proportion of forest in these plots where dark is high and light is low. You can see that's heterogeneous across the region. And we've actually classified Landsat every other year starting in 1999 in this region to try to get an idea of how those landscapes are changing through time. And not only are we calculating proportion of forest, but also landscape metrics to get at some idea of the heterogeneity within those landscapes. Now we're also interested in what's happening at the broader spatial scale. So these are the forest inventory and analysis plots in Minnesota. They're run by the Forest Service. These are revisited on a rolling basis by actual people going out in the field and seeing what's on the ground, the age and the species distributions within these stands. And by aggregating at a 16-kilometer radius, we get some idea of what the species diversity and the age is within the broader landscape centered around each of these plots. So this is sort of like a moving window moving across the landscape. And this is kind of what you might get. This is the proportion of forest older than 50 years in 2003. Again, dark is high proportion, light is low proportion. And here it is in 2012. Going back and forth between that, you can see that the landscape is definitely changing. The landscape tends to be getting older. But if you look at the delta of that, you can see it's not even across the landscape. There are places where it's getting a lot older, that's where it's in red, and places where it's a lot younger in dark green. And so because of this asymmetric change in the landscape, that might be driving some patterns we see in the wildlife. And as I mentioned before, temperature is a really important issue here. Here is the 2009 mean maximum July temperature, and this is from the PRISM website. And here, the thermoneutral zone for moose in the summertime is between about 17 and 24 degrees Celsius. This summer, things are pretty good for moose in Minnesota. Although there is some heterogeneity across space, it looked like it was pretty good. Compare that to 2012, it's pretty gnarly. This is pretty much every day of the month, the animals were getting stressed at some time of the day. So here's some preliminary results, and I stress that these are preliminary, so beware of thin ice. These are all the plots that are surveyed from 2005 to 2016. Of those 527 plots, these are the raw count data that we see with a smooth line going through them. And so, this is just raw counts and not adjusted at all, but how do we actually turn that into a population estimate? Well, I'm using a negative binomial regression in a hierarchical Bayesian framework. And importantly, we have random effects for year and for plot here. And here are some of the basic results. I don't have uncertainty on here, but these are all, the credible intervals for all these coefficients are not overlapping 0. So the important bit from the Landsat is that a really strong driver of population is the proportion of mixed forest. We found that the animals actually select for these when we do our relocation surveys of these animals. And there's a really high heterogeneity at those in that cover type. There's a mixture of deciduous and coniferous forests and also open areas. It's probably quite good for them. On the negative slope, we have water, which is the blue, that curved line, and also the amount of deciduous forest. They don't tend to like large amounts of deciduous forest in landscape. Using the forest inventory and analysis data at the very, very broad scale, the 16-kilometer scale, more young forest in that broader region meant more moose. And that's not surprising for an animal that likes to have young forest to chew on. But when we start looking at the distribution of cover types within those plots, if I start doing landscape scale analysis, 3 things pop out as being very important. The first is there are more moose in areas with larger mean patch areas of regenerating forest and also brushland. It's sort of in the same class. And fewer moose as in more complex, in areas with more complex patches of coniferous forest and forested wetlands. Areas with more curvy edges, there tended to be fewer moose. So what does this actually look like? How do we translate those numbers into maps? We'll look at that in just a minute. This is the final slope. This is the summer heat stress index, which is basically how many days above the thermoneutral zone it was in that block for that moose. As those numbers go up, the moose numbers go down. They don't like the heat. So this is an area predicted to have a very high population. What you can see here is up in this area, there's a lot of this sort of yellow, light green. That's all regenerating forest. So large patches of regenerating forest are high quality for this animal. This olive green here is mixed forest. Again, more mixed forest, more moose. And the dark green is coniferous forest, and they tend to be fairly cohesive, not very complex patches of coniferous. Compare that to a low population prediction area. Here it's dominated by coniferous forest with fairly complex edges. They tend to avoid that kind of landscape. So how well do we do? Well, this is the population trend that's being predicted by a completely different methodology. When we adjust our predictions for sitability, we pretty much nail that, and I'm pretty pleased with that result. So, okay, that's great. So we've managed to get this overall population trend. What does it look like on the ground? Well, here are the predictions. We'll go through time, starting in 2005. If I can click on it, there we go. What you'll see here is that overall population is just going to decline to blue, and then pop back up a little bit at the very end. And so, the important thing here is that all places are not equal. There are some places that are doing well, others that are not doing so well. So what are the next steps? We're interested in linking diet to landscape and how that might drive variation. To do that, we have to understand what these animals actually eat. To do that, we're using stable isotope analysis of hair. This is hair taken from the withers region at both capture and at death. And we can use that by comparing to the stable isotope composition in the forage to try to get estimates of what's going on in the springtime and what's going on in the fall in terms of their diet. Those are just made up numbers there. The actual proportions are here, and these are from 3 different regions, the warmer region, a more moderate region, and the colder region. And what I want you to see here is that they're just really different diets. In the warm region, they're eating a lot more of aquatic vegetation, that's the other class. And in the cold region, they're eating a lot of the more medium quality forage. So, in summary, how do we do, and what are the future implications here? Changes in landscape composition appear to affect moose populations. The complexity is important in predicting what's going on with those populations, but those landscape effects are only responsible for a portion of that decline. However, I think it's a really important tool. It's one of the few tools we have as managers to be able to affect change in these populations, changing what's going on in the landscape. diet and movement can link landscapes to survival and fecundity, but to really test this, we need to do some empirical work where we actually test how landscape change is directly linked to populations. Thank you very much.
Time for 1 or 2 questions.
Sure.
Thank you. Very interesting. That's mainly out of personal interest. Do you know if the European moose differs in ecology from the American moose, or like if these results can be directly applied to European moose populations?
I don't know. I mean, for example, in Sweden, they harvest more moose every year than we have, like by a lot. So I don't really know how they're actually doing. I know they are starting to worry about the decline, but I don't think it's nearly as bad. So I'm not really sure what the implications are over there until we start seeing a greater decline.
Yeah, I had one question. For that second to last slide with the diets, I'm just curious if the distribution of the resources is different in those different warm and cool environments, and that's why they're selecting them, or is it really like a diet shift?
So that's a really great question. And it turns out that we have data on that, and the distributions are not the same, but they don't reflect the diet that they have. And so especially that aquatic diet, it's just not, that's a real big change from what they're doing everywhere else. Lakes are pretty much equally abundant, but those diets are quite different.
All right. Okay. Yeah, okay.
This is the last talk.
Possibly, I'm a non-moose person, although I have seen one. Are they possibly eating more of the aquatic vegetation simply because they have to spend so much time in the water to help thermoregulate?
Yeah, so one of our hypotheses is that they are actually, on these hot days, spending a lot more time in the water and therefore eating that aquatic forage, which tends to be lower quality. They might also have a sodium deficiency in those areas for some reason or the other, and that's one way that they get a lot more of their sodium is by eating those aquatic plants. All right, thanks, folks.